Dettol is a disinfectant containing the antiseptic chloroxylenol, shown below. Part A. Chloroxylenol is a weak Bronsted-Lowry acid. Part 1. What is the systematic name of chloroxylenol? Firstly, we need to look for the longest carbon chain when working out the systematic name. That's going to be our phenol ring. So that means our name is going to finish with phenol. And then we look at the side chains. So we've got two methyl groups and we've got a chlorine group or a chloro group. The chloro group is attached at carbon number 4 and the methyl groups are attached at carbon number 3 and 5. So that means when writing its name is going to be 4-chloro to show that we've got a chlorine on carbon number 4. Then 3,5-dimethyl. It's important we write dimethyl because there are two methyl groups. And then finally phenol. To get the mark for this question, you must have the correct systematic name. So 4-chloro, 3,5-dimethyl phenol. This gets you the mark for this question. Part 2. Predict the number of peaks in a carbon-13 NMR spectrum for chloroxylenol. Firstly, when looking for peaks in a carbon-13 NMR spectrum, we need to look if the molecule is symmetrical. This molecule is, we can draw a line of symmetry here. So when labelling its peaks on carbon-13, we're going to have less than if we just count up all the carbons. So what I mean is we're going to have 1, and then 2, 3, 4, and finally 5. These are going to be our different peaks on the carbon-13 NMR spectrum. So that means we write 5 on the answer line provided. To get the mark for this question, you must write 5. Part 3. Name the functional group responsible for the acidity of chloroxylenol and describe a simple test which would confirm the presence of this group. The functional group responsible for the acidity of chloroxylenol is a phenol functional group. So we then need to write the test for a phenol functional group, and that means that with an indicator it's going to turn red or orange, and with a pH meter it would read below 7, so that shows that it's an acid. And then we need to say that it would have no reaction with sodium carbonate, or just a carbonate ion would do. To get the 2 marks for this question, you get a mark for writing phenol, and then you get a mark for saying that it would turn indicator red or orange, and that there's no reaction with sodium carbonate, or a carbonate ion. Part 4. A student measures the pH of the contents in a bottle of Dettol as 5.14. The label on the bottle shows the percentage of chloroxylenol in Dettol as 4.80%, i.e. 100 centimeters cubed of Dettol contains 4.80 grams of chloroxylenol. Assume the following. Chloroxylenol is the only acidic component in Dettol. Chloroxylenol is a weak monobasic acid. The density of Dettol is 1.00 grams per centimeter cubed. Write the equation using molecular formulae for the acid dissociation of chloroxylenol. Calculate the acid dissociation constant, Ka, for chloroxylenol. Firstly, we need to write an equation, and we're going to write a dissociation equation. So we're going to have our chloroxylenol, which is C8H9ClO, and that's going to dissociate to produce H plus and C8H8ClO minus. So this is the equation we're going to base our acid dissociation on. Next, we need to work out the RFM, or the relative formula mass, of our chloroxylenol. So that would be 12 times 8 plus 9 plus 35.5 plus 16, and that equals 156.5 grams per mole. Now we're going to use an equation triangle. We're going to use two equation triangles. We're going to use moles is equal to volume times concentration, and we're going to use mass is equal to moles times the relative formula mass. And we're also going to use the general expression for Ka, which is H plus squared over HA. Now typically we wouldn't write this squared, and we would write H plus and A minus divided by HA. But we can assume that the concentration of H plus and the concentration of A minus are the same because the solution isn't especially diluted or concentrated, and therefore we write the squared, which makes our calculations a bit easier. So what we want to work out is we want to work out HA. So firstly, what we need to do is work out the moles of HA. So that would be 4.8 divided by 156.5. So this is me using the 4.8 grams of chloroxylenol, and then I'm going to use 100 centimeters cubed as my volume when I work out concentration. But first let's work out moles, and that moles equals 0.03067 moles. And then working out concentration, we would do 0.03067 divided by 100 times 10 to the negative 3, because we're converting centimeters cubed into decimeters cubed. And that equals 0.3067 moles per decimeter cubed. And that equals our concentration of HA. Now we're going to plug this in to our expression for Ka. And if we did this, we're left with needing to find out H plus. So let's do this first. So the equation we're going to be using is that H plus equals 10 to the minus pH. So what we would do is we would do H plus equals 10 to the minus 5.14, because that's the pH we've been given in the question. And then that would equal 7.244 times 10 to the negative 6 moles per decimeter cubed. Plugging all of this into Ka, we get Ka equals 7.244 times 10 to the negative 6 squared divided by 0.3067, and that equals 1.71 times 10 to the negative 10 moles per decimeter cubed. So to get the marks for this question, you get a mark for correctly writing your equation for the dissociation of chloroxylenol. You get a mark for working out the relative formula mass of chloroxylenol correctly, so 156.5. You get a mark for working out the concentration of HA, so 0.3067 moles per decimeter cubed. You get a mark for working out the concentration of H plus correctly, 7.244 times 10 to the negative 6. And then you get a mark for working out Ka correctly, so 1.71 times 10 to the negative 10. Part B. Dettol contains other chemicals including A-terapinol, shown below. Part 1. A-terapinol is a chiral compound. Show with an asterisk the chiral center or centers in the structure of a terrapineal? So a chiral center is a carbon that has 4 different functional groups attached. So that's what we're looking for in this compound. So the only carbon that has 4 different functional groups attached is this carbon here. So we can label that with an asterisk. To get the mark for this question, you must correctly label this one chiral center with an asterisk. Part 2. A terrapineal meets the requirements for EZ isomerism. However, only one EZ isomer of a terrapineal exists. Explain why a terrapineal meets the requirements for EZ isomerism, whether a terrapineal is an E or Z isomer, why only one E/Z isomer of a terrapineal exists. Answering the first bullet point, there's a carbon-carbon double bond. And because there's a carbon-carbon double bond, we then need to go into more detail about why it can be EZ. And that is because each carbon has 2 different groups attached and therefore undergoes EZ isomerism or meets the requirements of EZ isomerism. Then we next need to say that EZ isomerism is linked to highest priority groups. So EZ isomerism linked to high priority groups. So that means you determine if it's E or Z based on the priority of the groups. So we need to look at our compound and determine where the highest priority groups are. So the highest priority group is here and here because we've got a hydrogen attached and a methyl group attached, and they are lower priority than the rest of the ring system. And so as both priority groups are on the same side, it's a Z isomer. And we can remember this because if we draw a Z isomer, then we have a person and they look like they're in bed, and we can draw a few Z's. And then E isomerism, well, if we drew an E isomer and we had a person, well, it looks like an easy chair, like Joey's easy chair from Friends. So finishing the bullet point, we have a Z isomer, and that is because the highest priority groups are on the same side. Another way of remembering this is same side. That's a common way of remembering this as well. So highest priority groups are on the same side. Finally, answering the final bullet point, we only get one EZ isomer because otherwise the ring would be strained. So to get the 4 marks for this question, so you get a mark for saying that it has a carbon-carbon double bond, a mark for saying that each carbon has 2 different groups, a mark for saying that EZ isomerism is linked to high priority groups, a mark for saying that Z isomer is existing here because the highest priority groups are on the same side, and a mark for saying that the ring would be strained. So there's a possible 4 marks for 5 marking points. So therefore, you don't have to say one of these marking points to get 4 marks, but it is useful to say all 5 for your own understanding. Part 3. A terrapineal contains 2 functional groups. For each functional group, choose a reagent that reacts with that group only. Draw the structures of the organic products of the reactions. Show the structures for organic compounds. Our first functional group is here. And this functional group is known as an alkene. Our second functional group is here, and this is what's known as a tertiary alcohol. It's known as a tertiary alcohol because it's connected to 1, 2, 3 R groups. So firstly, let's look at the reagents for an alkene. We can react this with bromine, or Br2, and that would be electrophilic addition mechanism, and we would get rid of our alkene functional group, and we would get a bromine attached to either side, but the rest of the molecule would stay the same. So this is our product that we would get with an alkene reacting with bromine. Then for a tertiary alcohol, we could react with CH3COOH and an acid catalyst. So this is esterification with ethanoic acid. So that means we're going to produce an ester where our alcohol group was. So the rest of the molecule stays the same, but our alcohol group becomes an ester. So if we drew the ester link here, this is what our organic product would look like. To get the 4 marks for this question, you get 2 marks for each reagent, functional group, and structure of organic product that's correct. So we would get a mark for reacting our alkene and producing 2 bromines, or a dihaloalkane, and a mark for showing our ester functional group with our tertiary alcohol. And then a mark for saying that you're going to have bromine reacting with the alkene and ethanoic acid and an acid catalyst reacting with our tertiary alcohol. Those are both worth a mark as well.